Hello and welcome back to Calculus 1 Saturday edition, where we are talking about derivatives. This is 3.3 Rules of Differentiation. Before we go into the lecture, the word differentiation means the process of taking the derivative, which is changing one function into another function. So the word differentiation is the process of taking the derivative, or changing one function into another. Let's write it down. Maybe I should say the act of taking the derivative or whatever. The derivative changes the function. And if you look at what we had before, when you had your function, let's say f of x is x cubed, I'm going to regret this, but whatever, x cubed minus 2x, we had to use the formula which we wrote down, which was the difference quotient formula. H goes to 0, so f of x plus h minus f of x over h. So this was the formula which we used last time to find the derivative, and that procedure was lengthy because there was a lot of algebra involved. So we had to start with a limit and copy this limit in every step along the way. We had to, well, actually, let's just say x plus h cubed minus 2 times x plus h, and then minus the original function, and all of that divided by h. So that was the setup, and we keep copying the limit throughout this calculation. So now we have to cube this one. If you know the formula, you can just put it down because it's Algebra 1 formula that you can memorize. And if you don't know it, then FOIL it on the side and bring all of the terms in. It's going to be x cubed plus 3x squared h plus 3xh squared plus h cubed. Those of you who are into learning the formula, note that your x's drop in power as ages rise in power. Ages rise in power. So you have a single x and 0 ages, and then x goes down to 2, and then 1, and then 0 exponent, and age goes 0, 1, 2, 3. And your coefficients are 1, 3, 3, 1. If you know Pascal's triangle, you know all of the coefficients for any exponent on this one. Pascal's triangle, look it up. It's a really cool feature that gives you all of the coefficients for your whatever the exponent is for the binomial expansion. All right, so that's that, and then minus x cubed plus 2x. Oh, I forgot this term. Oops, there is this thing. So minus 2x minus 2h, and then minus x cubed plus 2x. There we go, much better. So now this cancels. This negative 2x and the positive 2x, negative x cubed, positive x cubed are gone. And the only terms that are left are the terms that have an h in them. And I can factor that h out, giving us 3x squared plus 3xh plus h squared minus 2 divided by h. And that's what cancels the h, giving us, when each h goes to 0, kills those terms, 3x squared minus 2. This was the procedure we embraced last class, and this was the procedure to find the derivative. But it's a lot of work, and we would like to see if there are faster ways of doing this, which is what today's lecture 3.3 is all about. The way to take the derivative, this is the way to take the derivative, right? But what we are going to learn is formulas which are shortcuts. And you have to memorize those formulas. And I'm going to remind you when, the situation when you did that in the past. So if you think about 3 times 6 equals 18, that's something you memorized. What is the meaning of 3 times 6? It is 6 plus 6 is 12, and then plus another 6 is 18. So instead of when you have repeated addition, in this case 6 plus 6 plus 6, right? If you have the situation, you know that you can use the shortcut that you memorize, which you call multiplication, and you can get to that result either by adding each one of these numbers separately, or you memorize the shortcut and then you just know that 3 times 6 is 18. So now if someone asks you, 100 plus 100 plus 100 plus 100, you would say 4 times 100 is 400, because, right, you can do that. So this is what today's lecture is about. I'm going to give you rules. If the function looks like this, this is the way you take the derivative. And that will allow you to skip all of this work. If you don't want to learn today's lecture of, shorthand taking derivatives, then you will have to take all of your derivatives using the limit method, right? So, and we don't want to. So we're going to, maybe you do, I don't know, maybe you like pain, but most of the people don't want to do that. They want to go and deal with this way. All right, so now what I am going to do is I'm going to give you guys the rules. So the first rule is, and here comes the new notation, the derivative of the constant is 0. And I'm going to box this rule, and then I'm going to point the arrow. So the derivative, there is a multiplication there that you read of constant is 0. Can anyone tell me what the derivative, what is the purpose of the derivative? What does it do? Last time we said, what does it measure? We did that last
I think
one.
it was the slope of the tangent line to the
That's
graph.
correct. That's the mathematics. But if we are to, say
Oh, the change.
Yes, beautiful. And how much change do you have in a constant?
None.
None. See? So this makes sense, right? The derivative of the constant is always 0, because if you can read the derivative, or you can also say the change of the constant. Wait, it's constant. Constant is a concept. Constant doesn't change, right? So the derivative of the constant is 0. The derivative of the change is 0. Sorry, the derivative of the constant. The change of constant. There we go. The change of constant is 0. The derivative of the constant is 0. So if I want to take the derivative, and this is a Leibniz notation, it's a mathematician who also discovered calculus parallel to Newton at the same time. So this is the Leibniz notation, and it says the derivative of 4 is 0. And the graph for that is fairly simple, right? Because you have straight line at 4, and that line doesn't change anywhere. There is no slope. The slope is 0, right? Do we all agree that slope is 0 for the horizontal line? So,
Yeah.
and we know that the slope of the line, right, is the derivative. So slope being 0 means the derivative is 0. So that's the first rule. The derivative of a constant is 0. Now we're getting into the very important one. The derivative of x to the n is equal to the n x to the n minus 1. So this is what you are memorizing as a rule. Well, this is like a multiplication table of times 5, right? So you memorize all of those numbers. So here is the derivative for this, and it's very straightforward to use. You know, your n is going to be some kind of number or a fraction, and you just plug it for n on the other side and simplify, and that's it. So if I say, what's the derivative of x to the 8th, what would you say?
7x to the 7th.
8x to the 7th.
8x to the 7th, yes.
My bad, sorry.
Yep, because our n is copied, right? N is copied, and then n minus 1 is the 7. Okay, cool. And how about the derivative of a square root of x?
Make it to the 1/2.
Nice. We copy this and make the exponent a half, and then just unleash the formula. So copy the n, which is 1/2, and then x to the negative 1/2. Right?
Yeah.
And finally, how about the derivative of 1 over x to the 6?
Will it be negative x? No, negative 7x to the negative 8.
Negative 7.
Negative 7. My bad. Oh, because you're subtracting. My bad.
So let's copy it first. So what should be the x to the what exponent?
X to the negative 6.
Negative 6. So we drop down negative 6 as is, right? Because the formula says copy n as is. And then x to
Negative 7.
negative 7. Good. So
would you want us to put it? Yeah, I was going to ask if you want to.
Yeah, we're going to do this because it makes it better when we see it in a formula. This one formula covered polynomials, right? X to any integer. It covered all of the square roots, not just square root, a cube root and a fourth root, because how does the problem change if I have a fifth root of x? This is 1/5, right? So any root is taken care of this formula, and then we also have rational functions here, which is at the end. So 3 different types of functions are covered with this formula. So we have polynomial, radical, rational. So learning this one rule knocks off 3 functions. And polynomial is a huge group, right? Because you have constant inside, you also have linear function, quadratic, cubic, like all of those functions. Your entire pre-calculus chapter 2 is in this one little piece when you include 2.6 for rational, right? And then also the roots. So polynomial, x to the n. I don't want notifications, get lost. There we go, polynomial, radical, which is nth root of x, and rational, 1 over x to the n. So those are all different types of problems that you can cover with this. And now we're going to have another rule. We're just going to do the basic one. The more in-depth rule will be learned later for different bases. We have the exponential function, and that one stays the same. So that's our exponential function, which is really cool. And this is the only function that stays unchanged when you apply the derivative to it. So derivatives change one function into another function, but in case of e to the x, the function remains the same. And now we have the rules for differentiation, and these are insanely important because they allow you to deal with multiple functions at once. So one rule says that the derivative of f of x plus g of x is, just like limits, right? You can apply derivatives separately to each one of these. And that's going to be very useful. Now the next one is for subtraction, does the same thing. I could have done this in the same line, right? Just put plus minus up there, like I did for limits. And once I'm done with this, I'm going to talk about notation because I don't want anyone to be confused there. And finally, the constant rule is that if there is a number multiplied into a function, you can kick that outside that constant and just focus on the derivative of the function. So these are your rules for derivatives. And now we just need to do a lot of practice here and then talk about higher order derivatives, and then we're done. Now let's first understand notation, because it gets to be really frustrating when, you know, things are written incorrectly, because mathematics, as we talked about it, is very particular with its notation. So we don't actually have to learn a foreign language, right, to operate as engineers in a different country, because equations or notation is the same throughout the world. It's truly the unique language. The rules work in every country the same, and it's very important to understand the notation and use the proper notation. So we have two worlds. The world on the left is going to be f of x is given as x squared, and then you go into the new line and say f prime of x is equal to 2x, right? You use that rule that you draw pen in front, right? The power rule. You drop 2, and then 2 minus 1 is 1, so x to the first power. So this is your notation if you want to use f of x and f prime of x. Leibniz notation is better because you can do it in line. So you put equal 2x. So over here, you already have the derivative which is applied to this function to give you this answer on the other side. So you have the choice of writing one line the function, the next line the derivative, and you clearly cannot write this because that will be absolute garbage. This is not true. There's this quadratic on this side and linear, so you can't say that. We have seen so far that f of x is not the same as f prime of x unless you have e to the x. That's the only case. Only if you have e to the x, that's true. But for everything else, you know, thousands and thousands of functions, you know, this is it. So e to the x is the only one. If you have 2 to the x, it's already not equal. So this e to the x is so alone and so special in the world of mathematics. This is one of the parameters, obviously, for why it's so special, but it is really, really, really special to have that amount of power that, you know, your parenting function doesn't have that property or any other function in the world. So, and it never will be one. E to the x is the only one. So now we have this barrier between the two notations, and we'll be switching right from one world to another world. You say y equals x squared, you will have to say y prime equals 2x. There are no variations for this one. And most of the time, I am using the one on the right, and the reasons for that will be stated later in chapter 3, when I point out why this notation is better than the out of these 3 notations technically for the derivative. So you have 1, 2, and 3. The rainbow color, love it. This is absolutely the worst one of all. That's the worst one of all, and I am going to use it maybe in 2 lectures, 3 maybe, I don't know. But that's the worst notation of all of them. And most of the time, I will be using this as the best notation, and then followed by f prime, where we, where we have a little bit more flexibility. And I will try to stay away from this like a plague. Again, I have to explain that later. So now, if I want to say, find the derivative of 4x to the 6, we can write that problem as find the derivative, that's d dx, of is that multiplication, and then the function goes in here, giving you the problem d dx of 4x to the 6. And now you can use the rule. Did I label those 1, 2, 3? No, I didn't. I mean, I don't have to, but still. 1, 2, 3. I can use the rule 3 to kick 4 outside and just focus on the derivative of x to the 6. So that's, I'll just say rule 3. You'll find it up there. So what I do now is I take the derivative of this one, which is 6x to the 5. We said you drop the n power, right? And you subtract 1, so 6 minus 1 is 5. And then the total is 24x to the 5. Now you might ask me, are we allowed to go 6 times 4 is 24 and then bring it to 5 and have immediately the answer right there? Yes. And that's exactly what you will be doing starting the next class, right? When you practice this enough. We need to illustrate the mathematics in between that you will be skipping very soon because you will be doing so many of these derivatives. And then later in your coursework, obviously, not just math, but all of your engineering and hopefully physics, right? You will be taking these derivatives a lot, and then, multiplying this constantine that is just, copied, and then when the new constant pops in right here, then you have 4 times 6 is 24. So yes, you're allowed to jump all the way to the end. Another good example would be find the derivative of, let's say, 8 over x cubed. The fraction, right, stays unchanged. So if you want to copy this, again, I am writing a whole bunch of these intermediate steps that you might be skipping later on. I'm going to go and say this is actually 8 times 1 over x cubed. I'm going to write the gory detail now. All of these things will probably happen in your head. And then you just jump to the end. So this is where 8 goes in front of the derivative. And then you say 8. And then now this becomes negative 3 x to the negative 4, which gives you negative 24 divided by x to the positive 4 when you ship it in denominator. That's basic algebra there, right there. Oops. So this is your life now. You do not have to solve that complicated limit and grind through that ridiculous algebra, what you see in front of you now is actually the shortcut, right? So welcome to calculus. This is the shortcut. Now, most of you very soon should be able to do first step and then these two, keeping the other three steps in the head, right, as the intermediate steps. On your exam, this is for exam 2 now, not for the exam that will be reposted later. This, in exam 2, is your answer that you would type in Canvas, right? And whatever amount of steps you have in between would be on the paper that you email the pictures for, right? So you're allowed to go from there, but you need to have some steps in between, and depending on, right, your algebra knowledge, and right, you will have more or less steps. But I would say that, you know, pretty much these 3 steps, or maybe this one, like, or right, one of these 2, you know, you should have those 3 at minimum floating about, so we actually know, right, that you learn this.
I have a question.
Yes.
So for the test, when you said you plug in that for Canvas, does the Canvas, does the whatever it's called, the program or whatever, grade it, or is it up to you to see it and then?
That's what I tried to do with this exam, and that failed, right? I wanted the yeah. So the short answer to your question is no.
Okay.
So you will have to wait a day or two for the grade to be manually posted in the grade. So you would go into Canvas, you will click on grades, and the exam grade will. And I always post the announcement. So once the grades are up, I will just say, you know, in announcements, exam 1 is posted. Please go check your grades, and then we can discuss individual cases, right? Office hours and so on.
Yeah, no, because I was asking because I had a problem with my chem exam where I just plugged in the numbers, like the format, like I just did it wrong because it was the answer was correct, but the format was wrong. So that's what I was asking. Thank you.
All right, so here we go with this polynomial question. It's a quadratic polynomial here, and I'm actually going to give you a minute to solve this.
Professor, I know.
You have the answer already?
Yes.
What does it say?
Is it 6x plus 1?
Yes, very good. Now I am going to write the steps in between. Now obviously going to 6x plus 1 is exactly what we need for you guys to go later on, right? But now that we need to learn, you know, how this actually works, I'm going to say, okay, we have 3 and then the derivative of x squared, and then I have plus the derivative of x, and then I have plus the derivative of 6. So the first one is 3 times 2x plus the second one, derivative is 1, right? Derivative of x is 1, and then the derivative of constant is 0, which gives us, as you said, 6x plus 1. And that problem is solved. Now, before we go on, let's go orange. Why is the derivative of x 1?
Because you drop the exponent into the coefficient, and then your exponent becomes 0. Anything to the power of 0 is 1.
Well, x to the
Then you
power
get
of
1.
0 is 1. Later
Well,
on, we'll see that it's not anything really.
oh, okay.
But that's in chapters 4. So right now
Okay.
I'm gonna go with it, I'm just gonna say careful because we're gonna do later where, you know,
Got it. I'll forget that.
something raised to the 0 is gonna be like 3/4, and so it's like, wow, really? I
Okay.
learned it was always 1. Just like we're going to see that 0 divided by 0 is 3/2, so or something ridiculous like that, depending on what functions are at play. So yes, you are perfectly correct over here. So this
Nearly
is x.
correct. I was nearly correct. Not everything is, you know, he said.
Well, okay. So we have the dx, the derivative, and that's the 1. So 1 drops down, and then we have 1 minus 1, which gives us 1 times x to the 0, which gives us 1 times 1, which gives us 1, and that's how we get this 1. So the derivative of x is 1. You can, you know, remember that and roll with it at all times. So derivative of a constant is 0, derivative of x is 1, and then you have the other 3 rules, right? The polynomial rule, the E rule, and those 3 rules that are in there. Let's see one more of these. So the derivative of, and here we go. How about 4 over 6th root of x plus 3x to the 6. Let's do minus. We haven't done minus. Let's just put minus there because we can. All right, try that one.
Is it negative 24x to the negative 7th minus 18x to the 5th?
I think that's good. I think that's good. Let's take a look. Let's take a look at this together. So the first order of business is to separate these and kick the constants out. That way we have, so 4, the derivative of, and now this is x to the negative 1 over 6. Because root, right, gives us fractions, and then the order of the root is the denominator, which is 6, and it's negative because it was in the denominator. And then we have minus 3, and then we have the derivative of x to the 6. So this is the way we understand the problem. Now we just go through calculations. So we have 4, and then we have negative 1 over 6 over here, and then x to the, when you subtract 1, you get negative 7 over 6. And then minus 3, this is 6x to the 5 now. 4 and 6 cancels down to 2/3. So negative 2/3 x to the positive 7 over 6 minus 18 x to the 5.
I was wrong then.
Well, you didn't simplify, right? If I remember.
Oh yeah, okay.
But that's yeah. But when you simplify, I mean, again, this is the first time dealing with it. Just give it some time. You guys are going to be perfect with this. Let's pick one from the textbook and then say a few words of the higher order derivatives. So oh, those are dangerous ones. We'll get there later. Let's pick problem 33. This is the textbook example. They are asking you to take the derivative in respect to x of 10x to the fourth minus 32x plus e squared. I just remembered that I didn't change the title.
Professor, when simplifying e, we just leave it the same, correct?
Nope.
Okay.
E squared is a constant, isn't it?
Yes, very good. E is a number, e squared is a constant. Therefore, what's the derivative of it?
0.
Beautiful. All right, that was a trap right there. So what you have here is derivative is 40 x cubed minus 32. And this over here goes to 0 because, right, e is about 2.7. So when you square 2.7, you get less than 9, right? Because 3 squared is 9, so 2.7 squared has to be less than 9. So this is some number here that is smaller than 9. Well, I don't care what that number is. It's a number, and the derivative of a number is 0. Okay, cool. So here is evil stuff. The derivative of, and this is designed for you to make a mistake. It's literally designed for you to make a mistake. So think about the rules you had and the rules you did not have and what you must do to find this derivative. What kind of a problem is this?
Binomial.
Well, this is a binomial and this is a binomial, but then
Pi.
Quadruple. I don't know.
what kind of problem is this?
Multiplication.
Multiplication. Do we have a multiplication rule in this lecture?
No.
No.
So you just distribute right away then?
We're gonna have to FOIL.
Yes.
I think that's what he wants us to do.
Exactly. You must. You did not learn the product rule. It doesn't work. Parenthesis by parenthesis. So you cannot take independent derivatives and multiply them. You must FOIL in this case. You must FOIL and then take the derivative of that. So do that. Do that first. I'm answering the questions on the chat in YouTube.
Is it 18x squared plus 6x plus 4?
Oh, we'll have to FOIL first, right? Did you already finish that?
Yeah.
Oh, you're giving me the answer. Okay, so what was the answer at the end?
18x squared plus 6x plus 4. Sorry,
18x squared plus
6x
6x plus 4.
plus 4. Yep.
So once we FOIL this mess, we get 6x cubed plus 3x squared plus 4x plus 2. And yeah, that's 18x squared plus 6x plus 4. The derivative of 2 is 0. All right, cool. So we have this one. Here is another one. Also falls under evil stuff. These are problems 46 through 58. They have some great stuff in here. Oh, they are using w now as a variable. You can use anything as a variable. Do we have a division rule?
No.
No. Good. No. We do not have division rule. Which means you have to do what?
You can make it into 2 different fractions and then just take care of them individually.
Very good. Split the fraction and then simplify each fraction using algebra. Very good. And then take the derivative.
Hey, Professor, I was going to ask, if
Yes.
we're still on Zoom, does this mean that this lecture that you're doing right now, like right now today, is not going to be there in YouTube?
It is streamed live.
Oh.
I have 5 people watching it live on YouTube, plus you guys here on Zoom.
Okay,
so we might have a
perfect,
full
thank you.
class, between everyone. And I fixed the title now, so it is correct. It says Calculus1s 3.3. So you can watch this later on if you need to.
Thank you.
All right. So we're going to split this now into e to the 2w over e to the w plus e to the w over e to the w. And now you cancel this. I mean, if you can do this in 2 steps, it's okay, right? Whatever. But the whole thing should just be e to the w, right? Because the derivative of e to the x stays itself. Now, if you change the variable, it's still the same thing. You only have to be careful when this is a number, right? When that's a number, then it's when that thing is a number there, then you have constant. And derivative of 1, that's a derivative of a constant, which is 0. So we just have e to the w. All right, one more of these, and then we'll talk about higher order derivatives. So what is the derivative of, oops, we use the square brackets, square root of x times square root of x minus x to the 3/2. So just, to make it a little bit more annoying. Okay, so we have the first suggestion for the answer to be x minus 3x squared. Oh no, this is a simplified when you multiply. Yeah, okay. So when you take you have to multiply these two. So root x times x is x. And then when you have 3 halves plus 1 half is 4 halves, which is 2. So this is the problem that we have to solve when you simplify algebra. And the answer is the derivative of x is 1 and the derivative of x squared is 2x. One more concept. And then we are good to go. So let's realize that you start with a function, you take the derivative, and you change that function into another function. So you still have a function. Can you repeat the procedure of taking the derivative? The answer is yes. And how many times? As many times as you want. So we actually have a concept of the second derivative and a third derivative and a fourth derivative, which are called higher order derivatives. So if I have some kind of a function, f of x, that's a function. And then I have f prime of x, which is called the first derivative, or just the derivative. But then you have the second derivative and the third derivative. And then the fourth derivative. Now look at the notation, guys. Notation changes. Because we don't want to keep counting those tick marks. You don't want to see this. And then you go, okay, 1, 2, 3, then someone sneezes, then you have to start, right, counting again. So we change the notation into the order of the derivative to get to the what we will call the nth derivative. So you can do your linear algebra course, right, later on in peace. Nth order of the derivative, meaning you can go as high as it has to be a finite. You can't say infinite derivative, right? You have to say particular derivative, and for you to get to that derivative, you have to solve all previous derivatives. So this stuff over here, that's called the order of the derivative. Order of the derivative. Nth order as well, right? Now, every time you're taking the derivative, it's like taking the first derivative from scratch, right? So if you have your function to be given as f of x is equal to x to the 8 minus 6x squared plus 9, you can find the first derivative writing 8x to the 7 minus 12x, and then that's a 0, right, when you take the derivative. Is this a new function? Yes, it is. Can you take its derivative? Yes, you can. But that gives you the second derivative. 8 times 7 is, very good, x to the 6 minus 12. So now, can you take another first derivative? And the answer is yes, but that will give you the third derivative. Now, 6 times 50 is 300, so 336, x to the 5, and then minus 12. That's 0, so that's gone. Can you take the next derivative? Sure, right? The next derivative is the fourth derivative. And that's going to be 300 times 5, right? 300 times 5, and then 30 times 5, and then 6 times 5. So that's 1680 x to the 4. You can take the fifth derivative all the way. Eventually, look at your exponent. Eventually, it's going to die out. 7, 6, 5, 4, 3, 2, 1. Right? Constant, and the next derivative is 0. Now, does that mean that every derivative eventually trickles down to 0? No. No. Let me ask you a quick question. If I give you that f of x is equal to e to the x, what's the 137th derivative of x?
e to the x.
E to the x, exactly. Right? So, polynomials are the ones that in the derivative will go to 0. Everything else will accumulate, or e to the x will stay the same. And we'll see next Saturday that trigonometric functions, sine, cosine, and so on, because they're periodic, they will go in cycles, sine and cosine, and we'll see exactly why. Now, if you try to use this rule on f of x equals square root of x, we already seen that the first derivative was 1 over 2 root x. We had this before, right? Now, if you consider this as a function 1/2 x to the negative 1/2, what is the second derivative here? So take the derivative of this to obtain the second derivative. Ah.
Is it just 1 over the square root of x?
Well, let's see. We copy 1/2, then we drop down negative 1/2, and then we subtract 1. So it seems that it's negative 1/4, and then you have x to the 3/2 over here. So negative 1 over 4x to the 3/2. And as you can see, the power is growing. The power is growing as its derivative. So this what's the third derivative? What happened here? Sometimes tablets passes like this. So the third derivative, what would third derivative be? Well, the third derivative, listen to this, it's gonna make you go crazy. The third derivative is the first derivative of the second derivative. One more time. The third derivative is the first derivative of the second derivative. So all I need to do is to go to the second derivative and take the derivative, which is the first derivative, right? So I copy negative quarter. This is going to be x to the negative 3/2, right? Then I drop the power, and then I subtract 1, which will give me negative 5/2. So now this becomes 3/8, x to the 5/2. And as you can see, the power in denominator grows as you jump from one derivative to the next. So practicing and higher order derivatives, guys, are still the first. You always take only one derivative at a time. So the higher derivatives are always the first derivative of the previous derivative. So if you need to find the 56th, you never ever need to find the 56th derivative. We go to the third derivative at most. At most. If we want to be evil, we'll put the fourth one, right? But the application as well, you will see later on. You have your position function, and then the first derivative is going to be velocity, second acceleration, third derivative is jerk, and that's it. Like that, you don't go past that. Can you? Yes, but application. We'll talk about all of these things as we get there. So every single time I was just taking the first derivative of the line before. So if you need a 56th derivative, as I mentioned, you have to have a 55th derivative to get the 56th. But then in order to have a 55th to get the 56th, you have to have a 54th to get the 55th. And then all the way back to the original function. So 56th derivative means you are going to sit there and actually solve all 56 derivatives up to that point. This is it. I'm just going to show the higher derivative notation now, and the lecture is over. We're going to take, a couple of minutes break, and then when we come back, we'll do 3.4 and end for the day, so you guys can go review for the exam or ask questions about the exam. And I also have to repost the exam and all that stuff. So let's just quickly talk about higher order derivative notation. So we have, again, two worlds. There is the world that you have your f of x, and then you have your f prime of x on the new line, and the f double prime of x on the new line, going on through all possible lines. So that's one world, and that's the world we had. See that? F prime, f, right? And over here all the way to the fifth, and I defined it all the way through the nth derivative. The Leibniz world is not used as much, or almost at all, for higher derivatives. Leibniz world will be used for first derivative, and it will be used for word problems and a lot of good stuff in calculus. And here is why. It's, to write the second derivative, you would have to go d squared of dx squared of, let's say, 3x to the 6th, right? Now, if you pay attention to the notation and you know basic algebra, you would immediately say, oh, this is d over dx times d over dx of 3x to the 6th. So now, by order of operations, right, you do this one first. You copy this d over dx, and you have your 18x to the 5 in here, because that's your derivative of 3x to the 6. And now And that's equivalent to you doing first derivative, but you still have one more derivative to go, which was actually the second derivative, which is what you wanted, right? So now 5 times 10 is 50 plus 40 is 90. So we have our 90x to the 4. And it's okay to put, right, equal sign in between all of these because you literally do this in line. That's one of the powers of Leibniz notation. You don't have to start a separate line. You do the inline because the derivative is included with the function in the same line. Where over here, function is just given as a function. And you have to go to the new line to provide the derivative. So that's the notation, Leibniz notation. And then obviously, for Leibniz notation, you're going to have d to the n, dx to the n. So this is dx is like a unit, right? And one thing that I forgot to mention about the Leibniz notation, right? When you say that f prime of x can also be written as dy over dx, and then you can say d dx of y, but y is f of x. Maybe it also now kind of clicks in the Leibniz notation and how and why it behaves. So this is another way of noting the function, and over here, from here to this jump is y equal f of x from your pre-calculus 1 course. So that's also another thing about Leibniz notation. So this is the modern notation. I told you that Newton had this notation, and then we went into the prime, and then obviously this would be the next natural step because of pre-calculus 1. But truly the superior notation is what Leibniz wrote down, and sorry, not that one, this one. And that would be something that we are going to use a lot later on in word problems. So I'll be back at 10:10 with 3.4 on formulas for product and quotient rule for derivatives. So see you in 5.